Okay, so today we are going to talk about solving systems of equations graphically. So we should start out, what do I mean by a system of equations? So a system of equations is two or more equations, although for us typically we'll stick with two, um, both of whom have conditions that have to be met. And so what do I mean by that? I'll start out straightforwardly with an example out of your textbooks from page 428. This is example 2 on page 428, and I will apologize for the focus of this document camera. It should get a little bit better as I go along and record more. So, in this example, we are given two equations. 4x minus y plus 3 equals 0, and 2x squared plus 8x minus y plus 3 equals 0. And our focus is slowly getting a little bit better. There, that's better. Okay, so this is our system of equations. So we need both of these statements to be true, meaning whatever x and y are, 4 times x minus y plus 3 has to equal 0, and 2 times 8x squared plus 8 times x minus y plus 3 has to equal 0. That is the system of equations, and this would be what we would call, terrible curly braces, this would be what we would call a linear quadratic system of equations. Because one of them is linear and one of them is quadratic, although it may not look like that obviously from the time. So, a graphical solution to this will require your graphing calculator or some graphing calculator app that you might be using. So in order to find a solution, we are going to need to rearrange each of these equations for y. So if I take my first equation, I'll label these 1 and 2, make my life a little bit easier. So equation 1, 4x minus y plus 3. I want to get that y by itself. Probably the easiest thing to do would be to just add y to each side of this. So I can do that and have 4x plus 3 equals y. This focus is going to drive us all nutty, I think. These things. All right. Equation 2, I could do the same thing for and add y to each side of it. So I end up with 2x squared plus 8x plus 3 equals y. And at this point is when you're going to dig out your trusty graphing calculator. So first I'll show you what you can do with your calculator, and then second I will show you what I would like to see you have written down with it. So I'm going to y equals, do myself a couple of graphs. I'll get rid of the old graph that's there. And I'll make my first equation 4x plus 3. And I'll make my second equation 2x squared plus 8x plus 3. So we've got the two equations in. And if we look at a graph, we can see we have a couple of intersection points. Now, if you make your graph and you can't see the intersection points, it probably means you need to play around with your window settings a little bit. My window settings right now are sort of your standard negative 10 to 10 on both the x and the y. Which is not a bad place to start with these. You may find yourself needing to expand upon those or bring them back in depending on your graph. But that's a decent place to start, and we'll usually let you find something. Other hints are, we know in this case your y-intercept is around 3. So if your graph takes in y values of 3 when x values are around 0, then you'll see at least the y-intercept, and you can go from there. But in our case, we've got a nice graph with a couple of intersection points. So we know how to find those. I think people have seen this to this point, but we'll go over it again just to make sure. So if I do second function trace, that's the calc option, or the calculate menu, you'll notice option 5 is an intersection. Now the first couple of things it asks are first curve. You'll notice up top it's got what we put in for y1. So I'm just going to hit enter on that. For the second curve, you'll notice up here that it puts in what you put in for y2. So I'm just going to hit enter on that. Then it's going to ask for a guess. And when you've got more than one solution, it kind of matters where this cursor is. I'm going to move it down here. It doesn't have to be right on an intersection, but it's going to figure out whichever one the cursor is closer to. So I go down there and I press enter. That tells me exactly where that point is. It might be a little hard to read from this recording, but that's an x value of -2 and a y value of -5. And then I can just do second trace again, run through the process again. First curve is the same, second curve is the same, but my guess now I'm going to move the cursor up closer to the other point. Although I think since we know the y-intercept is 3 in each case, that's going to come out to be 3. Although, what we see here is fairly important. Your calculator did not give you 0 as the x value. It gave, a little hard to read on this, but it gave -9.42 times 10 to the -14. So if I show that just quickly here, -9.42 times 10 to the -14 would be -1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this thing is -9.42 times 10 to the -14. I think we can safely round that to 0. Oh, this focus. I'm going to find a way to make that better. Somehow. That seems to help for some reason. Okay. So, now that I know what my 2 points are, I need to write down something for me to see. So we can look at it later on. So, what I'm going to do is say here, using calculator. And we'll write down exactly what I called y1 and exactly what I called y2. I'm going to show a sketch of what that graph looked like. And I'm going to indicate the window settings that I had used for that. From -10 to 10, -10 to 10. Label my axes, of course. So then I had the y-intercepts of each at 3, and -2 and -5 was where the other intersection was. I had the line y1 going up through that. And I had the quadratic coming along like this. And I'm going to label those points that are of interest. Point at 0 and 3, and the point at -2 and -5. So then I'm going to say, using the intersect function, I found intersection points. -2, -5, and 0 and 3. So what this says to me are solutions for this series of equations, or system of equations. So I would say solutions are x equals -2, y equals -5, and x equals 0, y equals 3. So what I'm describing here are two separate solutions for that system of equations. It's worth noting that each pair represents one solution. Now, how you can verify that, in equation 1, using x equals -2 and y equals -5, 4x minus y plus 3 would equal 4 times -2 minus -5 plus 3. And if you work that all out, you get 0, which is what you should get out. And then to check it in 2 as well, 2x squared plus 8x minus y plus 3 equals 2 times -2 squared plus 8 times -2 minus -5 plus 3. And if I work that all out, I have 8 minus 16 is -8, minus -5 is -3, plus 3 is 0, which also checks out to what it's supposed to be. Each of these were supposed to work out to 0, and each of these did work out to 0. So that is a basic system of equations solved graphically sort of deal. So as I mentioned, this is a linear quadratic system of equations. Your book will refer to a quadratic system of equations by times, and all that means is that both equations come out to be quadratic rather than one linear and one quadratic. But other than that, you would do the same sort of thing. Now, this particular case we had two solutions, but it could have just as obviously been the case where we'd have one solution if these lines only hit in one spot. Or we could have had no solutions if, say, this straight line was dragged down to here. So linear quadratic and quadratic system of equations can have no solutions, one solution, or two solutions, depending on how many times they intersect. Okay, wanted to look at one more example dealing with a word problem, because everybody loves those. Pardon my high-tech setup here. This is example 4, page 430. Anyone having issues around not having a textbook, refer to the Google Classroom. Alright, so in this example we are applying a system of linear quadratic equations. Good times. And it describes engineers using vertical curves to improve the comfort and safety of roadways. Basically, if you're moving from one grade to another grade, it's kind of jarring to just do that in a V in a car, so they make a smooth curve instead to facilitate that. So, and the example in your textbook shows a diagram of this much better than I will, but if you've got one sharp grade, another sharp grade, just doing that in a car would be a little bit awkward. So they make a curved grade to connect the two. And you see you've got a line, and some curve like a quadratic going on in here. So, our two lines, as in the example, could be modeled by equations y equals -0.06x plus 2.6 y equals 0.09x plus 2.35, and the quadratic can be modeled with y equals 0.0045x squared plus 2.8. And we're asked to write out the systems of equations, basically move along to figure out each of these intersection points. So we're going to do that the same way that we did before, only now we'll have 3 equations to put in, and not all the solutions are going to be the same. So, again, for ease of this, I am going to call these graph 1, graph 2, and graph 3. So first, what that's going to look like on your calculator. Come in here, and I'm going to put in my first graph, negative 0.06x plus 2.6, 0.09x plus 2.35. Oop, I left some extra up there. Get rid of all that. 0.09x, 0.09x plus 2.35. Not 235, that won't be helpful. And the quadratic decimal 0.0045x squared plus 2.8. And my next task is going to be to find on my graph where all those hit each other. Well, that's convenient. Now it's a little hard to see how the quadratic's interacting with that, so I might change my window settings to take y values between 0 and 4. Let's see where that gets me. Drop that y scale down a little bit too. That looks a little bit easier to see what's going on. Okay, so obviously I'm interested in the 2 intersections here and here. So let's see if we can find those. Then we're going to do second trace, find the intersection, and now this is going to be important, what they call first curve and second curve. So my first curve, the one I'm on, is that first linear equation, y1. But what I wanted to intersect with is not y2, I want it to intersect with y3. So I'm just going to push the up arrow until I get to that curve. You'll notice now up top I'm on y3, and I'll press enter on that. And then my guess, doesn't really matter, I don't really need to move it, but it's over here somewhere. And it finds that intersection point for me. It's a little hard to read on there, but that's at about 6 2/3, or 6.67 and 3. I'm just going to jot these down off to the side for myself. 6.67 and 3. And then I'm going to go through the process again. Second trace, intersect. Now my first curve is not going to be y1 anymore, it's going to be y2. So I push down to there. Now this says y2 up top, I hit enter. My second curve is still the quadratic, which is what I want. I can see that as I move along, that I'm still in the quadratic. And then my guess, it doesn't really matter because the only place they intersect here is up this way, and I'll press enter. Oh, and it just barely catches it on the edge of the screen at 10 and 3.25. So then I will go through the same process that I said before. I am going to say, using my calculator, I set y1 equal to negative 0.06x plus 2.6. I set y2 equal to 0.09x plus 2.35. And I set y3 equal to 0.0045x squared plus 2.8. My graph on a scale of 1 to 4 x-axis going from -10 to 10. Pardon the freehand nature of these graphs. I'm estimating my intersections at -6 2/3 and 3, which is up here, and at 10 and 3.25. And at this point we can just roughly estimate from our graph where things are. And my first line, well, that's my second line, I guess. Second line and the quadratic. Smooth curve joining those 2 points. Our intersections were at 10, 3.25, and at about -6 2/3 and 3. Then I can say, using intersect, found the y1, y3 intersection at -6 2/3 and 3, and the y2, y3 intersection at 10 and 3.25. Now, our question doesn't give us very many units of measurement or anything like that, but what the points of intersection tell us in this case are pretty well where you've got to start your curved grade and end your curved grade at to make a fairly smooth transition from the first linear slope to the other linear slope. The intersection points represent where the curved grade joining the two linear grades must start and stop. So again, using your calculator is a fairly straightforward way to find these solutions, but I do expect to see these things in showing your work. Okay, that's about all I have to say about systems of equations at this point. There will be some suggestions for practice problems in the Google Classroom, and hopefully this was straightforward enough. I'll take any comments or questions in the Google Classroom. I probably won't look on YouTube for people's comments. That can be a bad zone. All right, everybody. Good luck. Stay safe out there.